Hi, I'm Bailey Laser, and I'm going to talk about PLA, PGA, polyphosphazines, how these polymers are used for skin tissue engineering. So skin is the body's first line of defense against harmful outside agents such as infection, radiation, temperature fluctuation, and water. Every year in the United States, there are 1.25 million burn-related injuries, 10,000 of which eventually lead to death. Many minor burns will heal on their own or can be treated by a skin graft, but more severe burns can cover a significant portion of the person's body, and which makes it much more difficult to treat. So the goal of tissue engineering is to provide a scaffold which fibroblasts and other body cells can infiltrate and form their own extracellular matrix, and then this polymer scaffold will dissolve away, leaving just the skin. So polyglycolic acid and polylactic acid, PGA and PLA, are created via ring opening polymerization from their dimers glycolide and lactide, and they degrade into glycolic and lactic acids through ester hydrolysis. The body can deal with both of these products extremely easily. It's routinely done, which makes the polymers very biocompatible aside from potential issues where acid accumulates from a large implant. PGA is more susceptible to water, and thus the hydrolysis will occur faster. Both experience bulk hydrolysis methods, which can be problematic in that the polymer will fail all at once instead of gradually. So both of these have the advantage that they've been used for decades and in sutures and whatnot, so they've got a wide history of use and are approved by the FDA. PLGA is the copolymer of PGA and PLA and can be very useful. It degrades much faster than either homopolymer, and we can tune this further by increasing glycolate content. A 50-50 mix of PLGA will degrade about 65% in 2 weeks versus a homopolymer PGA is only going to lose less than 50% over 6 weeks. So PLGA is much more relevant on physiological time frames. So as a scaffold, PLGA shows a similar elastic properties to skin, and we found that fibroblasts tend to proliferate best with a 350 to 1100 nanometer fiber diameter, which is close to collagen's diameter of 1500 nanometers. We've found that we can, by including growth factors prior to electrospinning our mat of PLGA fibers, we can create a fiber which will have growth factor at the core with PLGA surrounding it. And this will gradually release growth factor over the course of a couple weeks, which has been shown to significantly improve production of collagen, which obviously will improve eventual outcomes. Polyphosphazines are a newer class of polymers that are based on an alternating nitrogen phosphorus backbone, and with two side groups attached to the phosphorus. And from these side groups we can gain an enormous amount of diversity in properties because we can attach hundreds of different groups. Polyphosphazines are going to degrade into non-toxic products, phosphates and ammonia. We don't know exactly what's going on, but there does appear to be occurring by chain scission. So the side groups of polyphosphazine, we've investigated hundreds so far, and they can, this allows us to significantly tune the properties and get them exactly how we want for our final application. Many of them don't really work well for tissue engineering because they won't actually dissolve. Alkoxy and amine side groups seem to be the most promising in that they're hydrolytically unstable. Of those, amino acid ester side groups have shown to be the most popular. just the amino acid will leave the carboxyl group exposed, which can lead to unwanted cross-linking or uncontrolled degradation. So we use the amino acid esters. Again, this is biocompatible. It's going to degrade into the alcohol corresponding to the ester. So ethyl ester will yield ethanol, and then obviously the amino acid. We can control the degradation because hydrophilic groups will encourage water incursion, and versus hydrophobic groups, or larger side groups, which keep water out and slow the rate of degradation. There's also been some success attaching drugs to the sides. There hasn't been a whole lot of investigation here, but potentially could be useful in attaching, for example, anti-inflammatory drugs to improve the process. So finally, one application of polyphosphazines that's been investigated is to improve the material properties of PLGA. So again, PLGA breakdown can cause local acid buildup if you use too much of it, and since polyphosphazines break down into phosphates and ammonia, as well as the side group products, we can buffer out the acid. In addition, it could potentially, using certain polyphosphazines, slow down the degradation of, or slow down water incursion into PLGA, which would should shift degradation towards surface away from bulk and cause gradual instead of sudden failure. So to mix well, we have to use a polyphosphazine which will hydrogen bond to the ester oxygen and lactate or glycolate. There's a couple attempts that have been made are using glycine ethyl ester or dipeptide glycylglycine ethyl ester. We've also tried attaching tris in addition to glycylglycine ethyl ester. And so in that order, we've had increasing miscibility with PLGA. But adding tris made the mixture work better, but unfortunately caused the polyphosphazine to degrade slower than the PLGA, which negated the buffering. And the buffering wasn't all that strong with the first two. So there's a ways to go with this, but it does show significant promise. And in this PLGA degrading before polyphosphazine, we could potentially have a material which becomes more porous over time, which could be useful. So in conclusion, PGA, PLA, and PLGA have a long history of use and proven biocompatibility and have shown great promise for tissue engineering. Polyphosphazines, a newer class, are also extremely promising because they have a huge capacity to be tuned to the exact properties that we want by switching out the side groups. We've even been able to mix the two, which could potentially offset the problems with PLGA using the strengths of polyphosphazines. And we've still got a bit of a struggle ahead in order to get these fully where we want them to. So there needs to be further research into inserting growth factors in other drugs and reaching full compatibility, and continued research on tuning the properties in order to get towards the conditions we want. Here are my sources. Thank you.